Hello everyone, welcome back to our YouTube channel. The topic that we will be discussed today is electrostatic potential difference between 2 points. So first of all, let us go to the definition of this electrostatic potential difference. Electrostatic potential difference between 2 points is the amount of work done per unit positive test charge by an external agent in moving it without acceleration from one point to another against the electrostatic field along any path. So we have also learned earlier that if we have a charge say plus q and somewhere here there is a point P which is at a distance r from a charge plus q, the electric potential at this point is nothing but Vp. It is equal to 1 by 4 pi epsilon naught then q divided by r. How do we get this expression? We get this expression by finding the amount of work done in bringing a test charge from infinity to a point P. So that is Vp. It is the amount of work done in moving a unit test charge from infinity to a point P. So W infinity divided by Q naught is nothing but Vp. So now we want to find the electrostatic potential difference between 2 points. So first of all, let us consider a positive test charge Q located somewhere here at O. Say at any point A and B along this line, the potential at this point it is Vb, and the potential at this point A, say it is Va. Also, let the distance of a point B from O be Rb, and the distance of a point A from O, it is Ra. So if we make use of this equation, what is the potential at B? It is equal to 1 by 4 pi epsilon naught Q divided by Rb. And what is the electric potential at A? It is Va equal 1 by 4 pi epsilon naught Q divided by Ra. So how do we get this Vb? This Vb we can also write as W infinity B divided by Q naught. Also Va, it is W infinity A divided by Q naught. As we can see from here that Rb is smaller than Ra. From this figure, Rb is smaller than Ra. So clearly, we can say that Vb is greater than Va. Next, so what is the amount of work done in bringing a test charge from A to B divided by Q naught? W from A to B divided by Q naught, it is nothing but Vb minus Va. It is a potential difference between these 2 points A and B. So what is VB minus VA? VB minus VA, it is equal. Instead of VB, I'll put Q by 4 pi epsilon naught 1 by RB. Then instead of VA, I'll put Q by 4 pi epsilon naught 1 by RA. So this is the expressions of the potential difference between 2 points A and B, which is at a distance RB and RA respectively from a point plus Q. RB is distance of a point B from plus Q. RA is distance of a point A from plus Q. So this is the expression of the potential difference between 2 points B and A, which is at the distance RB and RA from plus Q respectively. Now we will discuss the relationship between electric potential and electric field. So first of all, let us consider a positive charge plus Q located somewhere here at this point. So let's draw a line like this. Say somewhere at this point B, the potential is VB, and somewhere here at a point A, the potential will be VA. From plus Q to a point B, the distance, say it is RB, and from point A to plus Q, the distance, it is RA. So since this charge is a plus Q, the electric field along this line, it is in this direction, and the electric field is represented by E. Now suppose we want to move a test charge Q naught from A to B. We need an external agent. So that external agent, in order to move a test charge Q naught from A to B without acceleration, it is nothing but F is equal minus Q naught E. So we will also consider that these 2 points B and A are very close to each other, so that the electric field at B and A is uniform. Suppose now we move this test charge Q naught in this direction, and the distance through which is moved, it is dl. In this direction, it is dl. So now the amount of work done in moving this test charge Q naught from A to B, it is nothing but it is equal to force dot dl. So if we substitute this value of force in this equation, we can write minus Q naught E dot dl. So as we can see from here, the direction of E as well as dl, they are opposite in direction. So the electric field, it is like this, dl is like this. So the angle between them is 180 degree. So Q naught, so E dot dl is nothing but E dl, then cos of the angle between E and dl, which is 180 degree. So this is equal to minus Q naught, so E dl, then cos of 180 is minus 1. So this is minus minus become plus, so Q naught E dl. So W AB divided by Q naught, it is equal to E dl. So here, as we can see from this figure, dl, it is in a direction of decreasing r. So dl, it is equal minus dr. Okay, as I have mentioned earlier, RA is distance of A from plus Q. RB is distance of a point B from plus Q. So this dl, it is in direction of decreasing r. We can say this, suppose this is dr. dr is like this along BA, but dl is this. So dl, it is in the direction of decreasing r. So we can write dl is equal minus dr. Now, WAB divided by Q naught, it is nothing but the potential difference between these 2 points. So what is WAB divided by Q naught? It is VB minus VA. WAB divided by Q naught is nothing but the potential difference between these 2 points. So VB minus VA is equal to E. Instead of DL, I'll put with dr. So what is VB minus VA? Is difference in potential. I'll put by dV. And this is minus E. I take dr to this side. I'll have dr. So this E is minus dV by dr. So this is the relationship between electric field and potential difference. So one should be noted that if you want to express this one in vector form, we can write E is equal minus grad of V. Here, this symbol is equal to I del del x plus j del del y plus k del del z. If we resolve this vector E into 3 components, we can write E equal Ex I cap, Ey j cap plus Ez k cap. And if we substitute this value of E in this equation, this value of del in this equation, this gradient in this equation, and if we equate left hand side and right hand side, we can write Ex is minus del V by del X, Ey equal minus del V by del Y, and Ez is equal minus del V by del Z. Having an idea about the relationship between electric field and electric potential, now we will solve some numerical problems. The first question says like this: the electric potential Vx in a region along the x-axis varies with distance x in meter according to the relation Vx is equal 4x square. The question is weighing us: calculate the force experienced by 1 microcharge coulomb charge placed at point x equal 2 meter. So solution: given Vx is equal 4x square, what we have to calculate? We have to calculate the force. That is, F is equal Q E. it is also given that Q it is equal 1 microcoulomb. So this is equal to 1 into 10 to the power minus 6 coulomb. We have also know that E is equal minus dV by dx. So if I put simply E, mod E, I'll have d dx of V. So this is equal to d dx. Instead of V, I'll put 4x squared. So what is this then? So this is equal d dx of 4x squared. 4 I'll take out. D dx of x squared, it is twice x. So this is 8x. So electric field at x equal 2 meter. This one 8 into 2 become 16. What's the unit of electric field? From here, volt per meter. So volt per meter. Now we want to calculate the force. So what is the force? Instead of a charge Q, I'll put 1 into 10 to the power minus 6. Instead of electric field, I'll put by 16. So this is nothing but 16 into 10 to the power minus 6. Since we have expressed the charge, which is in coulomb, which is in SI unit, and the electric field also in volt per meter, this one is also in SI unit. So the force is 16 into 10 to the power minus 6 Newton. So this is the force experienced by 1 microcoulomb charge. So the second question says like this. If the potential in the region of space near the point minus 2 meter, 4 meter, 6 meter is V equal 180x squared plus 60y squared volt, what are the three components of electric field at that point? That means we have to find the components of electric field, which is Ex. Then we have to find Ey, and we have also to find Ez. So we know that Ex is minus del V by del X. So this is minus del x. Instead of V, I'll put 180 x squared plus 60 y squared. So now this one is a partial derivative with respect to x. So minus del x of 180x, 180 I'll take out. Then del x of x squared, it is 2x. So since it is a partial derivative, so del x of y, it is 0. So the answer here, it is minus 2 into 0, 2 into 8, 16. So 360x. So what is Ex? What is Ex at x equal minus 2? This is equal to minus 360 multiplied by minus 2. So minus will become plus. 2 into 0, 2 into 6 become 12. 2 into 3, 6. So 720. What is the unit? It is volt per meter. So what is Ey? Ey, it is minus del x of V or del y of V. So this become minus del y. Instead of V, I'll put 180x squared plus 60y squared. So this become minus del y of 180x squared. It is 0. So del y of 60y squared, I'll have 60 with 2y. So this become minus 120y. So the electric field Ey at y equal 4 meter, it become 4 into 0. So 120 multiply 4. So 4 into 0, 4 into 2 is 8, 4 into 1 is 4. So minus 480. So again here it is volt per meter. But what is Ez? Ez, it is minus del del Z of V. There is no Z in V. Okay, as we can see from here, V is 180x square plus 60y square. So there is no Z. So therefore Ez, it is 0.